Well, this started out when I was working on my master's degree in agronomy, and my subject of study was decline in crops. Okay, what makes crop yield decrease over time, and what causes decline in trees? And I worked in Hawaii for a major companies in Hawaii to determine what was causing decline in macadamia. Okay, so my whole issue was why can't we maintain yield over time versus, let's say, slash and burn agriculture, or why do the yields go down over time, and how can we eliminate that? What are the limiting factors? There's limiting factors behind this, and what are they? And that was my project, to identify those factors. And the limiting factors that we determined based on other researchers like Dr. Vladimir Metachenkov, who was a member of the Russian Academy of Agricultural Science, and he was on special assignment to the Florida Institute of Agriculture. And the project was decline in citrus trees. Why is the million-acre citrus industry in Florida, reduced yield, quality, sugars, all those factors were going down? At the same time, I was working with crops in Hawaii. Same issue. Macadamia crops, decline in trees. Okay, so exchanging information and products, and we realized that the main limiting factors on a given soil was a lack of amorphous monosilicic acid and activated humic compounds. So in other words, soluble organic matter and a soluble form of silica. And so we found out that if you clear a rainforest, or any forest, it could be an oak forest here in Oregon, initially you have a fairly high availability of silica, silicic acid, in a form that's available, that can be translocated by plant roots. But it had to be in conjunction with fulvic acid, or humic acid, because humic acid is defined as soluble organic matter, and it's the living link between a dead mineral and a living root. Okay, so you had to have an intermediary organic component between an element like silica or phosphate and a plant root, which is a living cell, really. It's really living cells. So it turns out that after years of research in Florida and Hawaii by me, that it was determined that the main limiting factors in any given situation are lack of silica and in the form of monosilicic acid and activated humic compounds. And so we found out that when you replace those substances, you not only got better growth, you had resistance against diseases. Like, for instance, even viruses were reduced. Insect damage is reduced. And part of the reason is the silica is absorbed by the plant and tends to almost armor plate the leaf surface, the epidermis, with a substance which is defined as opal, which is another form of silica. Now, what's complicated about silica is it's got so many different forms. So you have silicon dioxide, which is sand, which is, not going to benefit plant growth. There's an organic component of microbial activity, organic matter decomposition, formation of humic substances, and their interaction with silica to form organic forms of silica, which can be translocated, can be absorbed by the root system, or as a foliar application. So that's why if you go to the rainforest or the third world in Central America or South America, and they clear rainforest and they get 2 years of corn, and then they have to push on and clear another acreage and burn it, and then they get another 2 years. And I worked with the Mayan Indians in Belize and found out that it took 20 years to get optimum yield. 20 years of brush, tree growth, before you could grow another crop of corn. Why did it take 20 years? And then they told me that if they just waited 10 years, they'd get about half a yield. So 20 years was optimum. And so we identified why that is, by testing the soil, testing the plants. It turned out that after corn production in a humid climate like that, with a lot of rainfall, a lot of oxidation and microbial activity, you basically lost your silicic acid and your humic substances in 2 years. And without soluble silicic acid, phosphate is not available. So you lost your phosphate availability. Okay, so it wasn't so much that the phosphate was definitely a limiting factor when you looked at the leaf analysis, but that's not the causative factor there. The causative factor was the leaching and changes in silica, in the formation of silica, in the form of silica, the molecular form that it's in versus, amorphous silicic acid versus silicon dioxide, which you can revert back to silicon dioxide without soluble organic matter, and that's just sand. Okay. But bottom line, just to try to get back to the main point here, is that's the main limiting factor of yield. And so once you deplete the soluble or the amorphous silicic acid or the plant available silica and humic substances, it's time to go to town and get a job versus unless you can go clear another acreage of rainforest. So the whole idea of this program is, no, we're not in a situation where we can't go slash and burning any more rainforest. We have to figure out what's happening with what we've already got and learn how to sustainably learn sustainable production on the same land instead of this constant slash and burn destruction, of the rainforest and just eating through it like ants. And basically, independently, in Florida and in Hawaii, we determined that it was the monosilicic acid and humic substances. Simple as that. So if you want to stay on your land and you want to return the yield and the quality factors, and it wasn't just yield, it was susceptibility to a whole range of pathogens, everything from powdery mildew to viruses to everything else. So silica acts as a protective, as an armor plating, you might say, that protects against fungal spore germination and establishment. The shiny surface of the leaf is obvious. If you're looking at silica or humic acid deficient crops, the leaf surface, for instance, on the citrus or the macadamia or whatever kind of crop it is going to have a dull appearance. It's going to have a dull green versus a shiny blue-green. So I can tell the difference immediately. And that shiny blue-green is what repels insects and also provides that opal coating that prevents a fungal spore from germinating and attaching or penetrating the epidermis of the leaf and into the cell, feeding off the cell. So you have a lot of factors there. And in some places of the world, like South Africa, they don't bother testing for phosphate without testing for silicic acid, because they know that if the silicic acid is low, it doesn't matter how much phosphate you use. So you really need to deal with the silicic acid before you deal with the phosphate. I mean, none of these things work in single factor approaches. They work together. Just like I say, if you have a phosphate availability problem, you tested the soil. You got high numbers for phosphate in the soil. Okay, but the plant leaf analysis showing low phosphate levels. Okay, do we throw more phosphate at it? You may already have, like I did tests in Idaho, and they were convinced that they needed phosphate. And I said, no, wait a minute. No, I don't think we need phosphate here. I think we need to be concerned with the availability of phosphate. And they said, no, we've got to use 80 units, 120 units a year phosphate. I said, okay, Let's just do a soil test where we measure total phosphate in the soil, not the usual available phosphate that the fertilizer companies offer and the universities offer. What's the total? Okay, so the available phosphate was around 8 to 10 parts per million. The total phosphate in the soil, this is southern Idaho, 2.5% organic matter, was 10,000 parts per million. So the problem wasn't lack of phosphate. It was the phosphate getting into the plant, So part of the problem was pH. And so if we used a highly silicious sulfur acidic product, which had a 13% silicic acid content, 20% sulfur with a pH of 2 or 1, about a pH of 1, we could reduce the pH from 8.3 down to 7.8, and we could increase the soluble silicate level. And then we also use humic substances, humic acid. Okay, no phosphate whatsoever. No phosphate whatsoever. Leaf levels of phosphate came up. The crop yields were higher than anybody can remember. We set yield records, in fact. So this idea of constantly throwing phosphate at the soil caused a tie-up of zinc. And so then you ended up having a zinc deficiency. So you've really got to look at the big picture, of how soil chemistry works. And it's just not dead chemistry. There's microbial activity involved. There's organic compounds, organic acids. There's a lot going on. And you have to look at the big picture. And silicates just cannot be ignored. I mean, if you want a healthy plant growth, reduce fertilizer costs, and all these other factors like powdery mildew, leaf funguses, blights, rust, etc., then you need that opal coating. You need a stronger epidermis to resist a fungal attack. And this is what silica applies. And this is why civilizations, after a certain number of years, go down the tubes. Basically, the length of these civilizations, the longevity of a civilization, is directly connected to the soil health, or the ability of the soil to produce food. Okay, so we're back to limiting factors. How does that happen? Okay, for one thing, the soil, after years and years of agricultural production, tillage, you oxidize the organic matter. And then the silicic acid or soluble silicates and other nutrients become tied up, let's say. In other words, they bind with other minerals and form insoluble complexes. So basically, you can connect the decline of all civilizations with a decline in soil health. And then there's specific limiting factors that cause that. And we've seen this throughout history, and we're seeing it now.